go for a moment to start. 6, 5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope. Swing note on the note.
Welcome to All Space Considered, everybody. It is Friday, June 3rd, the first Friday in June. We've got a great show for you tonight. As always, All Space Considered is brought to you by Griffith Observatory, the Department of Recreation and Parks, the City of Los Angeles, and we always like to thank Griffith Observatory Foundation, who's our nonprofit partner in so much of what we do. Tonight with me is Patrick So, and we also have Katie Flynn doing our pretty pictures and our space weather as well. And she's also my co-executive producer of this show and makes so much of this show happen. So we like to thank her extra. Also, we have Jared Head, who's going to take on the role of Out to Launch tonight. Chris is off getting ready for a well-deserved vacation. And we have a very special guest, Hubble Deputy Project Manager Jim Gilletic, with us to talk all things Hubble Space Telescope. So we're very lucky to have him with us tonight. And let's take a look at what we have in the show. Like I said, pretty pictures and solar system weather with Katie. We've got the sky report with Patrick. He's going to tell you about what's up in the sky, what we should be looking for, and a little bit about our lunar eclipse we just had. Out to Launch is going to be covered by Jared Head, and then I'm going to talk about the image of the black hole in the center of our galaxy, Sagittarius A star, is how we'll finish up tonight's show. So it should be a good one. Well, first of all, I want to talk about a recent result from the Hubble Space Telescope. And the Hubble Space Telescope, one of its stars, These are stars that get brighter and fainter and brighter and fainter, and the rate at which they do that tells you how bright they actually are. So if you just compare how bright they look in the sky, well, how bright they look in a Hubble image, you need a telescope like Hubble to see them, but you look in a Hubble Space Telescope image and compare the expected brightness versus what they actually look like, that tells you how far away these galaxies are. And this is what those light curves look like. Each of these little sort of, up and down curves, this almost a triangle wave pattern. Each of those is a different set of observations of a Cepheid star in each of these galaxies. And you can see they look similar, but they're not all quite the same. Now, what they do is they take local galaxies like the Milky Way, the Large Magellanic Cloud, Andromeda, which is M31, and NGC 4258, and they're able to use geometry to figure out how far away those are. They're able to use sort of local methods, and that starts this distance ladder. And then they're able to use the Cepheids to get the distances to the next set and compare that to the supernovae that are in those. So the type 1a supernova, it's a star that explodes, but they do so at the same brightness generally. They always explode equally bright everywhere in the universe. So again, that's known as the standard candle, and you can figure out how far away that galaxy is and compare it to the Cepheid. So those make kind of a one-to-one line there as well. And then lastly, they're able to go further out and use those type 1a supernovae much further away and compare that to their redshift. And the redshift is a measurement of the expansion of the universe. And that's the number they want to measure. Well, they got stretched out into the microwave background radiation, and you can see certain bright areas, certain dark areas, and depending on that pattern, the physics of the universe as we understand it predicts that the Hubble constant should have a value of like 67. So why are they different? 67.4 is the number they come up with. And these are different by a large amount. There's like a 1 in a million chance that these two methods would come up with a different value. So there's something real going on here. We know that based on this recent Hubble paper that's extremely good, they've looked into all the different places things could go wrong. They've calibrated things multiple ways. It's a really, really good paper. The error is only 1 kilometer per second in that 73. Well, the Planck value also claims to be super, super good and super narrow. So something's going on. There's a difference between the early universe and the nearby universe. And whether, my guess is we don't quite understand the physics of the universe and how our model of it is probably off a little bit, but it's a mystery. So astronomers, we love mysteries. It's why we're in this business. It's fun to try and figure this stuff out. And it just goes to show we don't have everything solved, but the Hubble Space Telescope is still doing amazing work after all these years. And tonight we have, with us, Jim Gilletic, the Deputy Project Manager of the Hubble Space Telescope, to tell us about NASA's incredible discovery machine, the story of the Hubble Space Telescope. So welcome, Jim. It's a pleasure to have you here tonight with us.
Thank you for having me. I'm sure it's going to be a great time. Lots of good stuff to tell you.
Wonderful. Let's get to it. And our audience is in for a treat here.
Okay. Well, you mentioned one discovery, or one of the main things that Hubble was actually developed for, one of the key projects when it was developed back in 1990, and that was to figure out the expansion rate of the universe, the Hubble constant. But Hubble's taken over 1.5 million observations to date. And we've had 20,000 plus papers that we produced on its discoveries. And as amazing as that is, 20,000 plus papers have been referenced in other papers over 1 million times. So the Hubble Space Telescope is still going strong. But the story of Hubble, however, in 1946, a very mild-mannered professor named Lyman Spitzer, who was at Yale University, he wrote a paper, and it was called The Advantages of an Extraterrestrial Observatory, or a telescope that would be put above the Earth's atmosphere. And he described what the advantages of those were scientifically. But he also made another very profound statement. And the profound statement in his paper was, it's not really, the value of this isn't just to expand our knowledge of what we already know, but it's going to discover these new phenomena that we haven't even yet imagined. And that's what Hubble's been doing. Now, I remind you that this was very early on. This is over a decade before Sputnik, the first satellite, was put into orbit. And it was also a dozen years before Hubble came around. But he would soon leave there and go to Princeton. And before NASA was around, I'm sorry, he would soon leave and go to Princeton, and he would team up with a guy named John Bacall. And he and John Bacall would start to lobby the astronomical community once NASA was formed, and said, hey, we should build this large space telescope. They would also start to lobby Congress. They would team up with somebody known as Nancy Grace Roman. She would be hired by NASA as the first executive woman at NASA. She was hired to start a space astronomy program. And she would lobby the higher ups at NASA, as well as try to get the astronomical community to come to a consensus on what this large space telescope should be. So in 1977, all their efforts came to a head, and President Gerald Ford signed into law what was known as the Large Space Telescope, that would later become the Hubble Space Telescope. So why do you put a telescope in space? Well, there's a bunch of advantages to doing that. First of all, you can see fainter objects. The atmosphere will cause light to kind of dissipate, and so you won't get all the light from a particular object that you're looking at from a telescope on the ground. You can see different wavelengths of light. So, in that particular case, ultraviolet light, for example, gets blocked by the ozone layer. That's a good thing for us on Earth, because that allows us to be able to block some of the cancer-causing light and helps us in terms of sunburns and stuff, a little prevention of sunburn along with your suntan lotion. But it allows us to see these types of things. And then you can also see, have standard viewing conditions, meaning they're the same from time to time to time. If you're on a mountaintop, you can have different weather, different higher atmospheric conditions, et cetera, that'll change some of the results that you get. You don't get that in space. It's consistent from observation to observation. And finally, you can see higher resolution. So let me give you a couple examples of these, and we'll start with the higher resolution. So if you can think of the Earth's atmosphere like a swimming pool, when you take the water out of a swimming pool, what you end up seeing are the straight black lines on the bottom of the pool. Okay, these black lines are your swim lanes, and they're perfectly straight. But when you put the water back in, you can see that they're not straight at all. And that's because the light from those is refracting and reflecting as it comes back up through the water to your eye. And the same thing happens to objects in the universe as its light tries to reach through the Earth's atmosphere to get to the telescopes on the ground. But you don't have that problem once you're in space. So I'm going to give you a very specific example of that to give you an idea of what kind of better resolution you get. In this particular image, you can see the moon in it. Below the moon is Venus, and above the moon, that dot that you can see is Jupiter. Now I'm going to show you a picture taken by an 8-inch telescope on the ground. This is just a quick snapshot through the telescope, but you get the idea. It's maybe something similar to maybe what Galileo would have seen 400 years ago. You can see the circle, that's Jupiter, and you can see a bunch of very bright stars. Those bright stars, of course, are the moons of Jupiter. Now, around the time of the launch of Hubble, there was a picture of Jupiter taken with an 8-foot telescope. Now, by 8 foot, I mean the 8-foot mirror. An 8-inch, I mean an 8-inch mirror. So the main mirror, which is your light collection mechanism in a telescope, the bigger the mirror, the more light you get, the more resolution you can get. This gives you an idea of an 8-inch telescope versus an 8-foot telescope. This one was on the Canary Islands. And of course, in this particular case in Jupiter, you can start to see the bands. You can see the red spot with a little bit more detail, et cetera. Now, if you take that 8-foot mirror and you put it above the Earth's atmosphere, like we did with Hubble, you then get this particular image. And here you can see all the grand detail of all those bands. And you can also see details on the moon. That's the moon Io. It's shadow reflecting onto or being cast onto the surface, upper atmosphere of Jupiter. And we're going to zoom in on Io because Hubble zoomed in on it once in ultraviolet light. and it actually caught a plume of a volcano that was going off on the surface of Io. So you get the idea of the dramatic advantage of fuel. They're going to glow. They're very, very hot, right? But they're not as bright as all the other stars. And astronomers wanted to understand and see how many of these were in a particular globular cluster. Now, a globular cluster is 100,000 stars all held together by their gravitational force. It's very difficult to see them. This is a ground-based image taken of the globular cluster, Messier 4, right? And then this is Hubble taking a small picture of a particular area. Before they took this picture, they only found maybe half a dozen of the globular clusters, the white dwarfs in the globular clusters. The circled objects are the white dwarfs. You can see how faint they are compared to the glowing stars that are still burning around them. Hubble found over 100 of them when they first started taking images of Messier 4. This is equivalent to standing on Earth and seeing a 4-watt nightlight on the surface of the moon. So this gives you an idea of how you can see fainter objects if you're above the Earth's atmosphere. The other example would be talking about the different wavelengths of light. Here is a picture of the Eagle Nebula, one of the most famous pictures ever taken by Hubble. This one was taken in 2015. The original was taken in 1994. This is a picture of the Eagle Nebula, which is, of course, the gas and dust that's left over of the star that exploded millions of years ago. This picture was taken in visible light, the light that your eye sees. But when you get above the Earth's atmosphere, you can see various wavelengths of infrared light that get blocked out by the atmosphere. So this is the same image, same years away, and that tower on your left is 5 light years tall, a light year being about 6 trillion miles. So it gives you the idea of the advantage of being above the Earth's atmosphere. So let's talk about Hubble itself for a minute. And I want to do that because, how do we take all these pictures? How does Hubble really work? How is it designed to work? The main part of Hubble is what we call the optical telescope assembly. Now, this isn't a set of trusses and mechanical beams and that hold the primary and secondary mirror in place and also holds the instruments in place. The primary mirror is an 8-foot mirror. It's made of ultra low expansion glass and it's curved. It's a concave shape. The secondary mirror is 12 inches and it's convex shaped. So the way this works is light comes down your tube, hits the concave mirror. Since it's curved, it forces the light toward a focal point, hits the secondary mirror, pushes it even closer toward a focal point through a hole in the primary mirror. Once it gets to a certain point, we stop it at about the size of a dinner plate, not at an actual focus point, and we pick off the light and take it into various instruments that are below it and to the side of it. From there on, inside the instruments, we have further mirrors that then it bounces off of and takes it to a focal point right in front of the detector. Those instruments, there are 4 of them found on the bottom. They're cameras and spectrographs. Spectrographs take the light and break it into basically a rainbow, and you can find bright lines in that rainbow. And depending on where those bright lines are, it'll tell you a lot of things about an object, what it's made of, if it's moving to you or away from you, how fast it's moving towards you or away from you, temperature, pressure. There's a lot of information in a spectrograph. These 4 instruments each are about the size of a very large refrigerator. They weigh about 800 to 1,000 pounds each. Now, around the outside of Hubble are 4 other instruments that we call radio instruments. The main one is Wide Field Camera 3. It's about the shape of a mini grand piano and weighs about 900 pounds, and it has 2 cameras in it. The camera takes ultraviolet and visible light pictures, and another camera that takes infrared light. Also around that outer side are 3 fine guidance sensors. Okay. These fine guidance sensors are again about the size of or shaped like a mini grand piano or kind of a pizza wedge, and they weigh about 400 pounds each. Now that's how we point Hubble. So if you want to take a picture of something, you have to give me 2 guide stars. You give me a guide star to the bottom of the object you want to take as an example, and maybe one to the right. We pick 2 of those 3 fine guidance sensors. They find those guide stars and they lock on. And those are the devices that can lock on so precisely and make sure that I don't move off those guide stars, that if I was to tape a laser pointer on Hubble, it could shine a laser on a dime and hold it on that dime, not just on the dime, but on the president's head on the dime over 200 miles away for up to 24 hours while I took the picture. So those fine guidance sensors are very precise, and that allows us to get these very, very, very sharp pointing requirements that we need to be able to take a look at objects that are in deep space. Around the center of Hubble are a lot of bay doors. They hold all the electronics that Hubble has and also contain some of the hardware for our point and control system. So by point and control, it's basically how do you turn Hubble? So the fine guidance sensors tell us and make sure that we're locked on and tell us if we're moving off a guide star, but to turn Hubble, to make sure we get to that guide star and make sure we stay locked on those guide stars that are around that picture, that object that we want to take a picture of, we use something called reaction wheels, and they use the one of Newton's law that for every action, there's an equal and opposite reaction. So those fine guidance sensors that you see one of the astronauts holding here are big wheels. They're about 2 feet wide. They weigh about 100 pounds each. And if you spin the wheel one way, Hubble's going to spin the other way. We have 4 of those wheels. They're kind of in a pyramid shape pattern on the vehicle, such that I can use any 3 to turn anywhere into space that we'd like to turn. Now, we have one other mechanism we use to turn Hubble, and that's something called magnetic torquer bars. On the outside of Hubble, there are 4 bars. They're about 8 feet long, 3 inches wide, and they have metal coils in them. And when you fire up those metal coils with electricity, they become magnets, and they use the Earth's magnetic field to pull or push Hubble in one direction or another. We also have solar arrays that produce about 5,000 watts of electricity. They're coupled with batteries that are inside so that we can power Hubble when it goes into the shadow of the Earth. We also have high gain antennas that allow us to communicate to communication satellites that are about 22,000 miles above Hubble. So we beam the images up to the communication satellites. They beam them down to White Sands, New Mexico, where there's a ground station, and then over to the Goddard Space Flight Center. And then we take those, make sure the data is all together, and push that up to the Space Telescope Science Institute in Baltimore, Maryland. And that's where the images then get further processed. And we also have an aperture door. So if we point too close to the sun by accident, the aperture door will close. I'm happy to say that in over 30 years of operations, that has never closed for that reason. There's one other major design to Hubble, which is why we're still here operating Hubble today, and that's servicing missions and servicing design. So how do you design a spacecraft to be maintained in space by astronauts? There are a bunch of things that are on Hubble that are very unique. We have these dishes that you see here on Hubble. One of them is connected to the robotic arm, and that's the exact purpose of them. The robotic arm can pick either of these 2 dishes, go up to them, and connect up to it to grab Hubble out of space and put it in the cargo bay of the space shuttle of it. Along Hubble, you'll see yellow handrails. You can see them circling the bottom and one running up the left side of the bottom. Those are there for the astronauts to be able to grab onto and tether onto if they need to get to a particular part of the spacecraft. For whatever reason, maybe there's too many close to each other. We then create special tools for them to use. So again, why do we do all this servicing? Why do we create Hubble to do this? Right. Well, there's a bunch of reasons. The first reason is we'd like to insert new scientific instruments, new cameras. When Hubble was launched, it had a 2.4 megapixel camera. Now it has 2 16 megapixel cameras that the astronauts have installed for us. We also want to take advantage of new technology. When Hubble was launched, we had tape recorders on board. That's how we recorded all the images, all the engineering data, all the science. We've replaced 3 of the batteries that are in one unit on Hubble. Just like on your car, your battery is going to wear out after some time and you need to replace it. We replaced the first set of batteries after 19 years. And so we're happy to say that the new batteries are still running very strong and giving us all the power that we need. And finally, you can correct problematic hardware. So the most famous thing of problematic hardware that people are aware of is something that happened to us at the very beginning known as spherical aberration. So let me kind of explain that to you. And I'm going to use, instead of mirrors, lenses, because it's a little easier to draw the lines and make you see the light pattern. If you have a lens and you have light coming in, you want that lens to be curved just right so that all the waves, all the light rays will come to a single focal point. But in spherical aberration situations like Hubble had, you're off by just a little bit of that curvature. And therefore, the light comes to multiple focus points. And that gives you blurred images. And that's what happened to Hubble. This is a picture of the core of Galaxy M100. You can see that it's very blurry. And that was because that the outside portions of Hubble weren't curved enough. It was off by 1/50th the width of a human hair. But that was enough to give us images that weren't very good. So that was pretty bad. We launched and we realized that all our images were going to be blurred. The public was mad. Congress was mad. Astronomers were mad, rightly so. The press had a field day with us. And then, of course, we were the butt of jokes and comic strips and late night television. Now, on top of all this, NASA had a lot of other problems back then in 1990. We had come off the Challenger disaster where the Space Shuttle Challenger had exploded shortly after launch, and we had lost all 7 astronauts. The shuttles were down again right before our launch in 1990 due to hydrogen leaks and other delays. They weren't hitting the 40-some launches a year that they had promised. So they were in trouble for that. NASA was also in trouble because the Galileo probe that was launched to go to Jupiter, the high gain antenna didn't deploy. So that meant that, it would have an impact on the science that they would be able to return to us once it got to Jupiter. And now you're sitting here with a almost, $2 billion, $1.5 to $2 billion telescope that's giving you blurred images. So a particular gentleman known as Ed Weiler, okay, he was the program scientist. He kind of reflected on this, and just so that you know, the talk in the hallways at the time was that NASA is going to cease to exist unless we figure out how to fix this problem. It's not going to exist as we know it today. It's like NASA's lost its way. So Ed Weiler was a no-nonsense kind of guy. He had been the program scientist for Hubble for years. He was hired by Nancy Grace Frohman, and he had a quote. And he basically said, whether we like it or not, this program is going to go down the history books, and we have to decide whether our grandchildren are going to read about it as a national disaster or a great American comeback. So the engineers put their heads together and they came up with what they felt was a solution. They figured out exactly how miscurved the mirror was. And so they came up with an idea for putting in what we'll call a pseudo instrument known as CoStar. Now that pseudo instrument, I call it pseudo because there was no camera or spectrograph or any other kind of scientific instrument into it. That little black triangle on the top corner there is actually where a robotic arm came out. And in that robotic arm, and this is a picture of it, you have these fingers that come out of the robotic arm. And on the ends of the fingers are little nickel-sized mirrors. They would intercept the light that came down, reflect off of the mirrors on the bottom, reflect off then the mirrors on the top, and go into each of the instruments. Those particular mirrors were curved to be corrective lenses, basically, and correct for the spherical aberration. We also installed another camera, which replaced the original workhorse camera. This camera is known as Wide-Field Planetary Camera 2, and it had the corrective mirrors embedded inside of it, so it didn't need the use of this arm. So once they installed this arm and deployed it, once they installed the new cameras, the first pictures came back. If you recall, I showed you this was a picture of the core of M100, the Galaxy M100 before with spherical aberration, and this was the picture of it after spherical aberration. Everything was perfectly in focus. After that, there was no stopping Hubble, and the discoveries just started to flow. In all, we had 5 servicing missions over time, where we did all kinds of stuff, repaired instruments, replaced broken parts, enhanced other technology such as computers and that. It's because of these servicing missions, without any question, that we're still in business today. So that gives you a little history of Hubble and how it's designed and how we've maintained it over the years. What I like to do now is just talk to you just briefly a little bit about the science behind Hubble. What are some of the big things, that Hubble has done over its 3 decades of operations? Well, the first thing it does is it studied stars, and specifically stellar nurseries. And in many of the nebulas that you see pictures of, there's often new star birth that comes out of the death of stars. And basically what you see are these balls of gas and dust that form out of the gas and dust that's left over from this dying or dead star. If they become big enough and enough pressure and heater in the middle, then a new nuclear fusion reaction will come out and a star will be born. This is the original picture from 1994 of the Eagle Nebula with the fingertips that you see up and down the left column. Those are potential stars, and including 2 that they actually were stars that they were able to verify. This is the first time we had seen star birth up close and personal, so it's kind of known as, it's been nicknamed the Pillars of Creation, and is by far one of the most famous images ever taken by Hubble. Hubble's also become famous for its pictures of nebulas, which again is showing really the end of life of the star. And a lot of them are nicknamed ones. So these are kind of fun ones. That's why I chose them to show you. The top left one is the Ring Nebula. The one next to that's called the Hourglass Nebula. Then you can go on to find the Cat's Eye Nebula. Below that on the second row, the really wide one is the Twin Jet Nebula, et cetera. So the astronomers have fun naming these, nicknaming these particular nebulas along with their formal names. But Hubble's allowed us to study star death and see how it actually occurs. Now, inside of these nebulas, not only do you have newborn stars, okay, but you also have planetary systems being formed. Now, this is a picture of the Orion Nebula. You can go out at night. You can see this with your naked eye if you're in a dark enough place in the country. And what we did when we zoomed in this particular part of the nebula is we found these guys. These are protoplanetary disks. These are stars with disks of gas and dust around them. The very bottom right shows one that you're looking at it on the side, so you can see it's a flat disk. The one that's above that on the right is, you're seeing that looking almost from the top down, so you can see the star with the disk around it. And this is where planets are formed, just like our solar system. So there was a theory that this is how planets were formed. We actually found the protoplanetary disks. So not only do we study the protoplanetary disks over the years, but we study something that was never imagined at all that we would ever study when Hubble was built and launched, and that was exoplanets. There weren't any exoplanets discovered at that time. But Hubble it's now one of its fortes where it actually goes. It doesn't necessarily discover the exoplanets, although it has discovered a few over the years. But what it does is it uses its spectrographs to study the atmospheres of those exoplanets. It has the ability to do that. And therefore, we can then start to search for planets that have some of the signatures that may show life, such as water in the atmosphere, or carbon or methane, and try to see if we could, especially around exoplanets that are what they call in the habitable zone. That means far enough from the star that it's not too hot, but close enough to the star that it's not too cold, similar to Earth. So we've been doing a lot of studies on a lot of these planets over the years. This is a particular picture of an exoplanet that I chose to show you, PDS 70b. And the reason I picked this one is this is the first ultraviolet image of an exoplanet ever taken. Now, I've kind of showed you a little bit of stuff in the Milky Way or deeper space, but we also study our own solar system, you know, the planets around our own star. This is a great shot of Jupiter. We actually did a 4K resolution version of Jupiter and made a video of it so that you could see it. But they've studied lots of things on Jupiter, including the Great Red Spot, which is, you know, a storm. It has been shrinking in terms of its width, not necessarily its height, but over the years. So they've been studying that to see how that has changed. They've studied the auroras at its poles over time. We've studied some of its moons, like in this case, this is Europa, where we saw plumes or geysers, basically, of water shooting out. We believe that's more evidence that there's probably an ocean underneath the icy crust of Europa. And we also studied Ganymede, which is, of course, the largest moon in the solar system. And we studied its auroras, and we found the auroras on it, actually. And it kind of shows that at least scientists believe that there's might be a salt ocean underneath its crust as well that's causing these auroras to occur. Now, I like to show you one other major discovery, which shows how we have coupled with other missions that NASA has done to help them become more effective. When I graduated high school, and even when Hubble was launched, Pluto had one moon, Charon. And of course, back then, Pluto was considered a planet. It hadn't been kicked out to become a dwarf planet yet. But Hubble went on to discover 4 more of its moons. And that was important because then we could study the orbits of those moons with Hubble. And so when the New Horizons spacecraft went out there, and I think it was around 2014 that it arrived, it was able then to take pictures of all those moons because it knew where they were going to be. Hubble would then go on to explore the Kuiper belt in that area so that the New Horizons could actually find an object, which we did find for it, that it could then change its course just slightly so that it could intercept it and then take pictures of a Kuiper belt object that's even deeper in space than Pluto is. So a lot of solar system work that goes on with Hubble is still going on today. Another forte of Hubble has been black holes. Hubble went on to help prove that black holes exist and that they exist in almost all at the center of almost all galaxies. This is the famous picture of a black hole jet coming out of the center of Messier 87, that particular elliptical galaxy. Another thing that Hubble is really famous for, and this might be, if you don't believe that the Eagle Nebula is the most famous picture of Hubble or one of the most famous, you definitely then would have to admit that the deep field pictures from Hubble are among their most famous. These are pictures in this particular case of a point in the sky that if you held a sewing needle at arm's length and looked through the sewing needle eye, that's how much the sky that this is a picture of. And we took a picture of an area where we didn't see much at all in it, other than a few foreground stars. It was pretty black. And we took a 10-day exposure. And when they did that, a lot of people thought we were nuts. A lot of people thought we were wasting time, precious Hubble observation time. But when they did that, this time we took a 1 million set. We have about 200 billion galaxies in the sky. There's also been a study done that says that's probably a low number because even Hubble can't see all the galaxies. James Webb, hopefully, will be able to see even more of them, and we'll talk about James Webb a little bit later. But if you do that math, they felt that there's probably, we underestimate by a factor of 10, and there's probably about 2 trillion galaxies. So we start again doing the math and thinking about how galaxies typically have hundreds of billions of stars in them, and you have that many galaxies in the universe, what are the chances that there may be life somewhere else in the universe? So the Hubble deep fields are extremely important. They also allow us to watch the evolution of galaxies over time because we can date all these galaxies to see how old they are. And that's helped in the area of galaxy evolution studies. We also are studying something called dark matter. Of course, dark matter is something we don't know exactly what it is, but you study it because of how it affects the things around it. In this particular image, in the center is a cluster of galaxies. When you combine that with dark matter, it actually bends space and time such that objects that are behind the galaxy that you wouldn't be able to see, actually their light gets bent around. It gets magnified and brightened so you can see that galaxy multiple times. And in this particular image, and I'm going to use a laser pointer here for 1 second. In this particular image, you can see this blue galaxy here. Here, there's another one here, there's another one here, and there's another one here. This is a galaxy that is 5 billion light years behind the galaxy cluster you see in the center, which is 5 billion light years from Earth and Hubble. We would never see that blue galaxy if it wasn't for a gravitational lensing effect that happens. This is nature's way of creating a telescope for us that we look into with our telescopes to see even further in space. So that galaxy, it allows us to see it. It allows us to see it magnified more than we could ever magnified, even if those galaxy clusters weren't in the way, and it allows us to study things. The important thing too, though, for dark matter is it allows us to do models and map where we believe the dark matter is to help better understand it and make models to understand when we see these different curves like this of galaxies that have been gravitationally lensed, we can get an idea where dark matter is located and where it's not. So Hubble's been big on the field of dark matter. And finally, of course, Hubble's been big on another kind of dark things, and specifically dark energy. We all know that we've known for a long time that the universe is expanding. That means everything's kind of moving away from each other. What we didn't realize was that expansion rate is accelerating. That was a surprise to us. And that was one of those things that Adam Rees discovered that David talked about his most recent work earlier during this particular show. This particular discovery then, dark energy, something has to be causing that acceleration. And so the discovery that rate is accelerating won three scientists the Nobel Prize, including Adam Rees, who's located there on the bottom. He's the leftmost of those three, and here he is getting his Nobel Prize for using both ground-based and Hubble data to make that determination. So Hubble's been, very, very much alive in all kinds of fields of astronomy. There's probably no field of astronomy that Hubble hasn't contributed to over the 30 years. And just to make you feel better, it's just a very young still field, our astronomical studies. And why do I say that? Hubble has seen only 0.1% of the sky with those 1.5 million observations. So there's a lot left out there for us to see and a lot left out there for us to discover. Now I want to change subjects just a little bit because there's another side of Hubble that people rarely know about. And that's one called technology transfer. That is, a lot of the technologies that was developed to make all these discoveries and make Hubble be the machine that it is, have helped us in our everyday lives. For example, when you get arthroscopic surgery, they put a camera, let's just say you have it in your knee, they'll put a camera in your knee and they'll be able to look at the area that they're performing the surgery on. That uses image processing algorithms that were developed for Hubble images. The scheduling software that we use to schedule all those observations throughout the year, that has been reused in the custom semiconductor industry to help expedite the development of semiconductors, and also in hospitals to help schedule all the different machines and all the different tests such as MRIs and CAT scans and that to make your stay shorter while you're in the hospital. The software that manages the overall processing of the images was reused by one company to help map the human genome. The star catalog that was created for Hubble was made into a sky map that is used on laptop computers by amateur astronomers. When you go into a hardware store and you give them a paint sample, a color sample, you say, hey, I want you to create a pint of paint for me that has this same color in it. They'll put it in a machine. That machine uses filters that were created for the Hubble Space Telescope cameras. The star mapping algorithms that we use are now used by wildlife conservations. In this particular picture, there's a whale shark. They have a dot pattern on their back. It's like a fingerprint that's unique to each whale shark. All you need to do is take a picture, and you can tell whether you've seen that whale shark before by using the star mapping algorithms. Our ultraviolet detectors are now used in mammography equipment in the fight against breast cancer. Our infrared detectors are used to help read ancient scrolls, including the Dead Sea Scrolls. Parts of the Dead Sea Scrolls have deteriorated over time, so when you look at certain segments, they appear completely black, they're unreadable. But when you look at them in infrared light, the further you go, they can appear almost as new, and you can read the scripts again. And finally, for those people who watched the Winter Olympics this past year, back in during the year that we had the Olympics in Salt Lake City, some of our speed skaters used the technology that we use to polish mirrors to polish their ice skates to make them faster. In this particular picture, it's Chris Witt winning a gold medal using that skates that use that technology. So Hubble has impacted you in many ways in your personal life that you may not be aware of. Now, because of all this that we've talked about today, the science, the technologies, the history, all that, Hubble has become really part of our pop culture. You can go out and you can buy videos, whether they're on a DVD or whether you're streaming something, which is documentaries on the Hubble mission or on Hubble science, or just flow through the Hubble pictures in a serene way. There are dozens and dozens and dozens of books that have been created on Hubble from by astronauts, by scientists, coffee table books of the images. We've been on hundreds of covers of magazines, both the images as well as the spacecraft itself, ones that you would never have guessed, such as Rolling Stones. People have used images from Hubble for stained glass windows in churches. This is a picture of a nebula taken by Hubble. That's the cover of an album by the group Pearl Jam. People use images of Hubble to make clothing. You'll find images of Hubble as well as the spacecraft on stamps on countries that have nothing to do with Hubble whatsoever. If you go down the street, you'll see a U-Haul truck, a moving van that has Hubble on the side. The pictures have been used for art exhibits in art galleries, while spectra that have been taken by Hubble have been used to create a laser light show that they show on the side of science centers. People have Hubble tattoos. And, I always say you're not anyone unless you've made it on a Google Doodle. Well, Hubble's made it on multiple Google Doodles over the years. And finally, in the last couple of years, the United States Mint has had a new program. It's the American Innovation Program, in which they have a coin for each state, and they dedicate that coin to innovation. The Maryland one was selected the Hubble Space Telescope to be on the coin. So these are just some of the things that you can show we're in the pop culture, but we're also in it because, if you went to Hollywood and you looked at some of the TV shows from yesteryear, like Star Trek Voyager, you'll see Hubble images in the background. The Hubble astronauts were on the show Tool Time, which was actually Home Improvement, but that was the show that was in the series Home Improvement. You'll see pictures in the Big Bang all the time, and posters from Hubble that we've developed hanging on the walls in the background of the offices of the people in the Big Bang show. And you see it in movies. Unfortunately, you see it in the movie Gravity being kind of destroyed. So that one isn't one of our more popular movies among our team. But lately, we did see it on the most recent movie by Ryan Reynolds, which is The Adams Project. You do see a picture of Hubble when they enter the lecture hall, the physics lecture hall. So Hubble is kind of everywhere. And it's really embedded in our culture for all these reasons. Now, whether it's due to the challenges that we had at the very beginning, where we had to overcome spherical aberration and the success in doing that, or the servicing missions that everybody has seen over time, where they could actually see the astronauts working on it, or the science discoveries that were made, or the technology that has helped you in your everyday life, or the pop culture and seeing a picture of Hubble on a coffee cup or whatever the reasons, or maybe it's just these incredibly gorgeous images that have not only changed our understanding of the universe, but changed how we see the universe in a way that we never imagined that it looked. Whatever the reason is, Hubble has secured its place in history, but its future is bright. We still have redundancy in most of its major systems. And those that we don't have, we're looking at ways to work around that. So if we did have a problem, we could still continue to do science. So we're hopeful that we'll be able to keep Hubble making groundbreaking observations well into the end of this decade, if not into the next decade. Now that's important because, of course, on December 25th, you saw that James Webb Space Telescope was launched, and that is a follow-on mission to Hubble, where Hubble sees mostly ultraviolet light and visible light, a little bit of near infrared. James Webb is focused on the infrared part of the spectrum. And scientists want to use both spacecraft together for as long as possible so that you can see the same object in all those different wavelengths of light. You can get a lot more information on it and see overall, get the characteristics of that object or that phenomena. So we're here to be in business for as long as we can. Headquarters will fund us as long as we are making groundbreaking discoveries, which we plan on being able to do for years to come. So since Hubble's continuing its mission, if you like to follow us, I suggest you follow us online at nasa.gov/Hubble, or you can follow us on our social media at NASA Hubble and find out about the latest discoveries as they come out. So thank you for having me.
Well, you're very welcome. Thank you for that wonderful overview of the Hubble Space Telescope. It's easy for us to take for granted what Hubble has brought us over these decades, and seeing it all in one place, all at one time is really quite amazing. Also, I'm going to wave my own flag here a little bit. Thank you for talking about the white dwarf work. I actually joined that team after they did M4, and we went and got observations of 47 Tuc and also of NGC 6397. We did both of those clusters as well and did the white dwarf cooling sequence. I got to do all the planning, so seeing how those planning tools are used in hospitals is super cool as well. But thank you for mentioning that work and including it with some of the important work Hubble did. That's very exciting. Now, we've had lots of great questions from our audience out there, but I have one question. Is there any chance that Hubble could get serviced again? We're building these new vehicles that are going up there. Elon Musk wants to build the Starship. Any chance that Hubble could still be serviced? Would it be worth it?
So there's always a chance. There's nothing planned, though, or on the books at the moment, and I don't see anything coming. The reason is because you really needed to have the space shuttle. We would take up thousands and thousands and thousands of pounds worth of equipment, whether they be tools or replacement hardware. Plus you had a place and you could actually take Hubble and put it in the cargo bay and hold it still while the astronauts worked on it, et cetera. So if you wanted to do that, you would have to overcome those things and build that capability into the new spacecraft, whether it be the Starliner, whether it be SpaceX, et cetera. So there would have to be some project that would have to be a conscious project that would be Congress and everybody would be willing to fund to do that. And there are no plans on doing that. What they want to do at the moment is they'd rather take that money. Similarly to when they shut down the space shuttle, they used that money to create these, to create Artemis and the spacecraft to get us back to the moon, to help fund the commercial crew, which is the SpaceX missions and the Boeing missions. So similarly, they want to take money and rather than spend it on trying to go up and fix Hubble again or enhance Hubble again, try to build a replacement for Hubble. And that at the moment, though, we don't see that happening until probably the 2040 time period.
Yeah, of course, we're going to get the Nancy Grace Roman telescope, but it's a whole different kind of telescope. It's more for surveys and wide field. It really is, it won't have the capabilities that Hubble will have. Patrick and Jared, I think you're out there somewhere too, and also Katie. Do any of you have any questions for Jim?
Yeah, I have a question. Last year, Hubble's payload computer it shut down unexpectedly, and I was just wondering, with how do engineers troubleshoot and fix these problems with the Space Telescope that's almost 300 miles above Earth, and it's going around the Earth 90 times, 90 times every time, 90 minutes around the Earth?
It's a great question because sometimes I'm always fascinated with how we figure things out myself. The answer is you do two things or three things really. Is first of all, you take a look at all the telemetry, all the data that comes down to the ground, and you study it like crazy, number one. Number two, you take a look at all the design diagrams and documents that you have for that particular hardware. Try to make sure you understand exactly how it works and should work and see if that telemetry matches. And then the third thing you do is you do experiments on board. So you try powering this on and then powering this off, or trying doing this test with this particular device or not. In the case of the computer, we powered it up, but nothing, we couldn't seem to get the memory to work. So we thought, must that be a problem with the memory module? So we then went and tried another memory module and the same thing. We still couldn't get the memory to work. We're like, wow, that's unusual. So then we tried a third memory module and said, well, if it's a bus related thing, and the bus is the wires that that you transfer the information to the memory from the main central processing unit, the CPU of the computer, maybe it's that. So we'll try a different memory module on the backup bus. We tried that, still couldn't get anything to work. So then they said, okay, well, it can't be all these memory modules aren't working. It can't be all these buses aren't working. It can't be all the computer isn't working. So what's in common? And through analysis, you figure out, well, it's the power supply. And so,
yeah, go ahead.
So anyhow, so that's what we realized. And then we went over and powered up the backup power supply, and everything seemed to work.
Yeah. A quick question from some of our folks out on the YouTube chat. One, Jonathan wanted to know, how much longer could HST last? And then Jared, you can join us here. You can ask the next question. So how much longer would HST last now, assuming we can't refurbish it? What are you thinking?
Well, it's a great question. And I like to answer that question by always asking the person who asks it, how long is your car going to last until it breaks? And there's just no way to know, because you don't know what's going to break next. You can do some statistical analysis, which we have done in the past, and we continue to do to try to figure out what's the things we have to worry about the most. But you don't really know. You're in a harsh environment of space with a lot of radiation, with a lot of heat, a lot of cold, et cetera. So our best guess is that because we have the redundancy that we have, that we'll probably be able to make it to the end of this decade, if not longer.
Okay. Another question. Well, Jared, go ahead. You popped in here, and everybody welcome Jared, who's going to be talking about out to launch with us. But what question do you have for Jim?
Yeah, being a hardware guy myself, Hubble's been amazing because with the ability of the shuttle to bring hardware from Hubble back and get that to analyze it, it's helped out a lot in the materials development and some other things with developing electronics and other systems. So I was wondering, what are some of the lessons from Hubble that have been learned that are going to be incorporated into the design of future space telescopes?
Well, one of them you see on James Webb, and that is you don't want to have spherical aberration. And if you do, how are you going to fix it? So James Webb has all kinds of actuators behind all the mirror segments. So, you can tilt each of those mirror segments and move them around. And not only that, if I'm correct, I believe they have one in the middle that you can actually deform the mirror surface, which we could not do on Hubble. So that's the easy one, I would say. I think there's redundancy. I think there's easier ways that technology allows you to do things. So in Hubble's case, because of the computers, and remember, we launched with a computer that had 72K of memory. We now have the main computer has been upgraded in 1999 by the scientists, and it now has 2 megabytes of memory in it, right? So we're more, so we were more limited on what we could do with the computer. So we're time-based. So every information we give them, we give them a plan, it's time-based. So at this time, do this, this time, do this, at this time, do this, at this time, do this. James Webb doesn't do that. I believe they're event-based. It says, hey, the next thing you want to do is do this. And however long it takes you, make sure you get that working, and then do the next step. And however long it takes you, and it can figure that out because it has the extra power to be able to do that kind of thinking and computations. So I think that's a lot of it. There was another interesting thing done. It may not be as applicable to telescopes, although it is that the Johnson Space Center, when we brought back Wide Field Planetary Camera 2, took the radiator panel that was exposed to space and basically cored out all the areas that had micrometeorites. So if you looked at it now, it looks like a piece of Swiss cheese because of all these holes that were in it, because they wanted to understand what was hitting Hubble. And that camera flew for 16 years. What hits it, what's the impact when it hits it, and learn as much as they can so they could do those types of things for other spacecraft and human spacecraft for the moon and Mars, and that to learn how to protect the spacecraft and its inhabitants as much as possible.
So is that one of the reasons why they're planning on deorbiting Hubble rather than just leaving it in a parking orbit? We had another viewer, Dave, wanted to know, why not just leave it in a parking orbit and then go service it when we get around to it? It would just be too damaged, or what's the reason we don't do that?
So that is an excellent question. It's a great question. The problem for Hubble is it has no thrusters. So the only way that you could raise it in orbit or lower it or change its orbit was with the space shuttle. So when we went up there for the servicing missions, on several of them at the end, we had it raise the orbit of Hubble higher again before it released it. So the problem for Hubble is that if it re-enters, because it has no thrusters, if it just re-enters somewhere and you don't know where, not all of Hubble's going to burn up in re-entry. Parts are made of titanium. That huge mirror may not completely burn up. It's made of glass. So there's a statistical probability that it could do damage if it comes over a populated area. It could do damage or maybe even hurt somebody. So we have the requirement, and on the last servicing mission, we put a little docking ring on the bottom of Hubble. We have the requirement that we have to attach a propulsion module to it so that we can do a controlled, either one of two things, a controlled reentry into the South Pacific where it's not populated and no damage would be done if anything didn't burn up, or raise it into a higher parking orbit, like 2,000 kilometers up. Right now, Hubble's about 540 kilometers up. That decision has not been made. Where it's not predicted that Hubble would re-enter until the mid to late 2030s at the earliest. So we're allowing, technology to kind of, continue to advance before we worry about actually designing and building one of those particular modules.
And then the last question I'll take from our audience, earlier, Astro Bill wanted to know if the launch of JWST would free up some Hubble time. I know that there is a little overlap on their instruments. Will astronomers all be applying for JWST time, and will Hubble focus on just the visible where it doesn't overlap? Or how will that affect observations for Hubble?
Well, it probably will affect in terms of, if you have a choice to use JWST or HST, JWST will give you a higher resolution because it has a bigger mirror. And when you hit those longer wavelengths, which is what infrared light is, it's longer than the visible and ultraviolet. You need a bigger mirror. It's something called diffraction limited to get that higher resolution. So they probably will do that. I don't think it's, it'll free up time, but remember, Hubble is oversubscribed. So every year when we go out with a call for proposals, for every 5 that gets submitted, 1 gets selected. And it's not because the other 4 or 5 or however many it is aren't good proposals. There's just not enough hours in the day to take the picture. So if it helps Hubble, that's great. But my bet is that with discoveries that James Webb is making and things of that nature, that Hubble's going to be overbooked even more because they're going to want to be taking pictures of that stuff too.
Yeah. Well, thank you so much for joining us. Absolutely fascinating. Everybody, make sure you follow NASA Hubble. The information's right there for you to follow them on Twitter and Facebook and the Instagram. And, we've really enjoyed talking with you, Jim. Fascinating to get that overview and to remember all the amazing discoveries that the Hubble Space Telescope has done and still is doing. To this day, you still see HST in a lot of these press releases that our astronomers are using this resource, which has been incredibly valuable to us. So thank you so much for joining us on All Space Considered. We really appreciate it.
Well, thank you for having me.
Yeah, absolutely. It's been amazing. And now we're going to move on to our next section. Get us forwarding here. I think it's time for some beautiful pictures out there. Katie, are you with us? There you are.
I am. Hello. So this first pretty picture we have is by Damian Peach. He took this one of our beautiful planet Saturn on May 23rd. And then this image was taken by Griffith Observatory telescope demonstrator Anthony Perkic. This is the Fireworks Galaxy, which is located in constellation Cygnus and about 22.5 million light years from Earth. And if you were able to view any meteors during the meteor shower on Monday night, this one was from Todd Kunioka, and I believe he was in Lake Mead, and this was from May 30th, just this past Monday. On to some solar system weather. This is our sun from May 10th with sunspot 3006 on the bottom center there. And this actually produced an X-class solar flare, causing radiation from the flare to ionize the top of Earth's atmosphere and actually cause a radio blackout over the Atlantic. And you can see where that happened here, and that lasted just over an hour. And this is a sunquake from the sun. And 26 years ago, researchers discovered the seismic activity on the sun. You can see those ripples there. And just recently, this was the first seismic activity sunquake from solar cycle 25, which is the cycle we're in now. And you can kind of see those ripples right in the middle of the image there. And then here we have a huge sunspot. This is 3014, and this video is a 24-hour period of it almost doubling in size. Each of the black spots you see there are larger than the width of Earth. And we'll zoom in on that large sunspot. You can see the storm swirling around in there. And what's interesting about the sunspot is that it is almost a third of the distance between the Earth and the moon. It's, I believe, 125 kilometers from end to end. And then here we have what was considered a dead sunspot in the bottom right there. And a dead sunspot is when a sunspot starts breaking apart, but this one actually was considered dead and then produced a flare that was an M-class flare headed toward Earth. and that was projected to get there by May 28th or 29th. This happened on the 25th. And then on the 28th, this image is from Mary Beth. This is the Mackinac Bridge in Michigan. And you can see some aurora right above it. And here's another image of that. So beautiful aurora over Michigan this week. And then this next video also of some aurora. This was during the lunar eclipse. This is from the South Pole, and that's actually the South Pole telescope there. So lunar eclipse happening with aurora, and you can see the Milky Way behind there too. So this, this video I did speed up, but it's just an incredible scenery to have viewed. And then here's a composite image of that. And that ends our pretty pictures in solar system weather.
Wow, that's just an amazing picture there from the South Pole. And in fact, objects do go around in a circle up there because you're at the South Pole. So the entire sky is just going around. And this is an amazing, you know, we get to see it. The lunar eclipses normally don't make a straight line like that. That's amazing stuff. Well, thank you, Katie. Always a pleasure to see these. And the space weather just keeps getting more exciting for us. So we'll look forward to we'll look forward to next month, but maybe the month after. We'll tell you more about that in a little bit, folks. Well, Patrick, now it's time to turn to our sky report. So what's up in the June sky for folks?
Okay, well, there is quite a lot going on, and just continuing on with the theme of the lunar eclipse that occurred on May 15th. We're just going to give you a recap of what happened as we observed it here at Griffith Observatory. This first picture shows the moon as it was in total eclipse from the roof of Griffith Observatory. It was a very beautiful sight. The weather was perfect. And the eclipse itself was an early one. So the lunar eclipse was already in progress as it rose from Los Angeles. And here you see the moon is roughly about 1/3 partially eclipsed in the dark shadow of the Earth, that dark area just hugging the horizon, which is also known as the belt of Venus. A lot of people gathered at the observatory to watch this spectacle. And so they were all treated to a very special event. And for those around the world, we streamed the eclipse through our telescope on the roof, through our streaming equipment. And over 500,000 viewers tuned in to watch our stream. And these included viewers from areas around the world where it was daytime, where they couldn't see the eclipse, and areas where it was clouded out. So here's how the eclipse unfolded in these series of pictures. Here we see the moon is partially eclipsed. The dark portion, the reddish portion, is in the Earth's umbra, the deepest part of the Earth's shadow, while the lighter portion on the right is still in the penumbra, the lighter portion of the Earth's shadow. So it's pretty bright. And as the eclipse progressed, we see that we're in the final minutes of totality as more of the umbra begins to slip across the moon as the moon moves into the Earth's shadow. Once that happened, the total eclipse, or the beginning of totality, began, and the moon was immersed in the Earth's umbra for 1.5 hours. That's a pretty long eclipse. At mid-eclipse or maximum eclipse, you can see that the northern part of the moon near the top there is much darker than the southern part. And that's because the northern part is closer to the center of the Earth's shadow. So there's a graduation of the umbra isn't quite uniformly dark. It graduates from very dark at the center and going lighter as you move to the edge, and the moon's span across the gradient of that shadow, and that's what you see. The moon's appearance was a lot darker than usual, so this was a pretty dark eclipse compared to other eclipses that we've seen. So this happened at 9:11 Pacific Daylight Time on May 15th. And of course, with these eclipses, all good things come to an end. And so we see here the ending of the totality and the brightening on the left edge of the moon. all in all, this was a great eclipse, and here's a sequence of it taken by one of our museum guides, David Pinsky. So it was really a great night for all of us. We have on our Griffith Observatory YouTube channel a time-lapse video. It's a 1-minute time-lapse of the entire eclipse sequence seen from Los Angeles. And also, if you want to watch the full 4-hour eclipse sequence as it unfolded, there's also a link for that as well. Now, if you've missed the May 15th lunar eclipse, you don't have to wait too long. There is another eclipse coming up on November 8th, and this is another total lunar eclipse, and it's visible in Asia, Australia, Pacific, and the Americas. And once again, we'll be at the ready with our streaming capability, and we're going to stream this eclipse as it occurs on the night of November 8th. With the eclipse and the excitement of the eclipse over, we turn to our evening sky and to see what we can see as we look towards the south on a June evening, kind of in the middle of June. And what we see are to the southwest, two constellations are constellations of the spring sky, Leo the Lion and Virgo the Maiden. And then we're kind of in a transition because just east of south are summer constellations. And these are Libra the Scales, Scorpius the Scorpion. And way down there, just emerging from the southeast, is the constellation Sagittarius the Archer. A little bit east of that is a constellation called Aquila the Eagle. Its brightest star is Alta. So the appearance of this constellation just above the eastern horizon really heralds the beginning of summer. And speaking of the beginning of summer, the summer solstice occurs at 2:14 a.m. PDT on June 21st. So this is the moment when the sun reaches the farthest northern point on its annual path, or ecliptic in the sky, as seen in the northern hemisphere. So from Los Angeles at local noon, which occurs at 12:55 p.m. PDT, the sun is 79 degrees above due south. This is the maximum noontime altitude for the entire year. The summer solstice marks the beginning of summer in the northern hemisphere and the beginning of winter in the southern hemisphere, so kind of opposite. And then, of course, that reverses when we have the winter solstice. Now, from the solstice, we will turn to the morning sky, because you're probably wondering, well, I don't see any planets in the evening sky, and that's because all the planets are all hiding out in the morning sky. And if you were to look just about 5 a.m., just about an hour before sunrise, you're going to see 5 planets visible in the east towards the southeast. We begin with the 2 planets closest to the horizon, the 2 innermost planets, which are seen in the east, Mercury and the brilliant planet Venus. A little bit higher up is the planet Mars. And then from the southeast towards the south, the planets Jupiter and Saturn, the large gas giant planets. The order of these planets really mimic the distance of the planets from the sun. So this is a great way to go out and see all these planets all together in the morning sky. And it's also a great opportunity for amateur astronomers and everyone else to observe and photograph these planets. And we're going to show you some recent photographs taken by amateur astronomers with a fairly large telescopes. This is the image of Venus in a gibbous phase, taken through a 14-inch telescope last month. Here we see a series of images taken through various filters, red, green, blue on the left, kind of black and white, and an infrared image as well. And when combined, you get a beautiful color image of the planet Mars with its southern polar cap seen at top. Now, not only can we see clearly some of the surface features of Mars, we can also see cloud bands and ovals on the planet Jupiter in its upper atmosphere. And these are visible even though Jupiter is at a distance of 760 million miles from Earth, which is kind of incredible to think about. But not only Jupiter is being observed here on the ground, but it's also being observed by the NASA's Juno spacecraft at close range. So Juno just made its 42nd close pass or perijove around Jupiter last month. And at its closest, it flies just about 2,200 miles above its cloud tops. And it does this every 43 days. So the last perijove was on May 23rd. And it has a unique orbit. And this is a picture taken on that perijove. It has a polar orbiting orbit where it can image Jupiter's north and south pole. These are areas of the planet that we can't see from Earth. And so this is a very unique view. Also, at its closest point, you can see intricate details such as these cumulus-like clouds, these white little pop-up cumulus clouds that are in this image here. And this picture was taken from a distance of 2,360 miles above the cloud tops of Jupiter, closer than any other spacecraft has ever been above the cloud tops of this gigantic planet. So this is truly amazing. And these details, you can just look at this picture for several minutes and just look at all the swells and the storms. It's just incredible. Another beautiful planet, which is within easy reach of a small telescope, of course, is the planet Saturn, and its rings show up very nicely. And so you don't really need a large telescope to image it, but if you do, you can see some of the features in its rings and, of course, the cloud bands around the planet Saturn. So let's go back to our morning sky, because on the 18th, the moon actually sweeps by these planets from between the 18th through to the 27th. So on the 18th, the waning gibbous moon is just about 4.5 degrees below Saturn. Just about 3 days later, the moon is reduced to a waning crescent, and it rests just about 3 degrees below the planet Jupiter. On the 24th, the crescent moon actually fills the gap between Venus and Mars, aligning itself with the rest of the planets. And this could be a really nice photographic moment for anyone who has a wide field lens to take a picture of the 5 planets, including the moon, all lined up together. So this is a really good day to mark your calendars if you want to get up early and get this really beautiful snapshot here. So after this, the moon moves towards dawn through to the 28th. And speaking of the moon, our moon phases this month. First quarter is on the 7th. And then we have full moon on the 14th. Last quarter is on the 20th. And new moon is on the 28th. So that's your sky report for this month. So go out and take a look at those wonderful arrangement of planets in the morning sky.
Well, thank you for that, Patrick. Lots of stuff to see, and it's good to see a perijove again, and just keeps taking amazing, amazing pictures of Jupiter. Really neat stuff. Well, Jared, you're here filling in for our very own Chris Butler, who is on a well-deserved vacation. So what's going on up there out to launch this month?
Well, boy, I got to say, Dr. Reitzel, there is a lot happening down at the Cape in Florida. And hopefully I can fill Chris's shoes. They're pretty big ones and pretty good ones to fill.
Well, I'll introduce you a little bit. Jared's one of our amazing museum guides at Griffith Observatory. And you are one of the people that's always rushing off to watch these rocket launches whenever they happen from Vandenberg. And you do an amazing job getting others excited about it. So you're the right man for the job. So take it away.
All right, thank you. And just going to be starting to talk about SpaceX's Falcon 9 and just how much it's actually been launching in the past month. So I want to start off actually in April, which is a little bit before the previous episode of All Space Considered. And that would have been on April 29th. It launched a Starlink mission then, and then we had another launch on May 6th. And yes, indeed, it was a Starlink. And then on the 13th, we had, you guessed it, another Starlink launch. This one, however, was not out of Florida. This one was through Vandenberg here in California. And we'll actually talk in just a little bit about what you can go see coming up in the next couple of months. And then the next day, it was actually less than 22 hours later, that quick turnaround to launch a Starlink out of the Cape. And then another 4 days later, SpaceX launched another Starlink out of the Cape. So basically really building out their satellite internet constellation as fast as they possibly can. And then just a couple more days later, they launched Transporter 5, which was a mission to deploy a multitude of small satellites, benefiting a lot of research groups and colleges and others. So this ridiculous cadence is something that has not been seen since the deep space age of the 1960s. We're talking 6 launches in 26 days from April 29th to May 25th. And if we really want to extend it out a little bit further, we could go all the way back to April 1st, and SpaceX has done 11 launches in 54 days. So they were talking about launching once every week this year, and they are well on their way to making that happen. So best of luck to them. And there will be a few launches coming up that you may want to keep your eyes on if you're going to be able to make it out to Vandenberg here in California. But I do want to talk about another spacecraft, a hopefully to be crewed spacecraft, and that would be Boeing's Starliner. Now, if you know anything about it as a part of the Commercial Crew Program, you know that it was going on a test flight back in December of 2019, and it had some issues with its mission elapsed time clock that caused Starliner to think it was in the wrong position. It fired its thrusters and burned through all of the fuel it would have used to dock with the International Space Station. They kept it on orbit. They were still able to do a lot of tests and did quite a few with flying colors. But when they were coming back, they separated the service module, and they almost had an incident where it would have recontacted or hit the heat shield on Starliner, and that would have been very bad. Luckily, they caught that before that would have happened, but still not great that that was going to happen to begin with. So the Orbital Flight Test 1 back in December 2019 was considered a partial failure, and Boeing agreed with NASA that they needed to refly it. So they were getting ready to do that last year in August, but they had a valve issue during the countdown, and they just couldn't figure it out. So they had to pull that Starliner off and go with another one. But luckily, finally, on May 19th, Starliner took off and went on its way to the International Space Station. Just 2 days later, on the 21st, it docked with the International Space Station, delivering just a couple 100 kilograms of payload and going to be taking home a couple 100 kilograms of payload as well. So this is pretty exciting because now we have 2 crewed vehicles here in the United States. We have SpaceX's Crew Dragon, and then pending certification, which should be coming relatively soon, Boeing's Starliner will also be able to carry crews. And in fact, if everything is given the A-OK by NASA, the next flight that Starliner does, hopefully before the end of the year, will carry that first crew on a crewed test flight to the International Space Station. Just a little bit of history here too. This is the first time a country has ever had 2 operational vehicles that could carry a crew at the same time. So Gemini and Apollo here in the United States was pretty close. And in the Soviet Union, you did have the Soyuz and Buran, their own version of the space shuttle at the same time. But Buran just flew a test flight. So to me, at least, it doesn't really count. So the United States here coming in and getting that first multi-crew vehicle thing with it. And then, as you mentioned, Dr. Reitzel, Orion coming up soon as well. So then we would have 3 crew-capable vehicles here in the United States. Well, after undocking on May 25th, Starliner returned to White Sands, New Mexico. And a Starliner is very interesting because it is a capsule, but it doesn't splash down in the ocean. It lands on land. So that means that they actually have airbags on the bottom of it. They deploy it and they cushion the landing down. So very, very cool that they have that capability to do that. And looking around the world for some launches that are coming up in just about a day. So on Sunday, not too far from now, China will be launching their next crew to their Tiangong space station, Shenzhou 14. So they'll be having 3 astronauts there. Also, a little bit later in their mission, they're actually going to have 2 new modules attached to the Tiangong space station, Miantan and Mengtian modules. They're going to increase the amount of area that the astronauts will be able to be in, and also increase the amount of area where they can put research panels and other scientific instrumentation for them to do that. Look for those launches sometime in July and October. We've also got NASA's Capstone spacecraft coming up. This is going to be launched on a Rocket Lab Electron, so a very small rocket, one of the smaller launchers here that you can purchase. It's going into an orbit around the moon that the Lunar Gateway, NASA's space station they're going to build around the moon, will be going into to test that out. So very exciting. We have a deep space mission that's being launched by a very small rocket with a very small spacecraft. So super exciting stuff with that. We like to talk about Psyche because it's going to the metal asteroid Psyche. It's been delayed. It was originally going to go in August of 2022. They found some issues that they want to handle. So they're going to go back about a month to September of 2022. It is launching on a Falcon Heavy, so should be able to handle that push to the right of a month pretty well. And then Space Launch System going to be rolling out once again to the pad to test it on June 5th, and that fueling test should occur sometime around June 19th. It'll actually start a couple days ahead of time on June 17th, but the fuel will be loaded on the 19th. And that's sort of the make or break of this test, because during the early one back in March, they had some issues with leaky valves and other systems. And to kind of look at the Vandenberg Space Force space schedule for all of our locals here in the Southern California, or really generally California area, we do have 4 launches coming up between now and August. All of their times are to be announced, but there are some days. We've got 2 Falcon 9s, one going on June 18th and another on July 5th. So those will be pretty interesting to go see, especially the one on June 18th, launching a satellite for the German military. That one, it's light enough that the first stage will actually return to landing zone 4. That means you will be able to see the first stage come back. So if there was one to go to, I'd recommend that one. Also, Firefly Aerospace will be trying again with their Alpha rocket, their mission to the black on July 17th. They tried back in September, had some problems, and had to activate the flight termination system and blow up their rocket. So hopefully they get to orbit on that one. And then a doozy that you're going to want to go see on August 1st, the National Reconnaissance Office will be launching NROL 91 on a Delta IV Heavy, and that will be the last Delta IV Heavy, the largest rocket that flies out of Vandenberg. So you're going to want to go catch that for sure. That one, don't miss it. It is an absolutely amazing rocket to be able to see in person. Yeah. And that is out to launch for you.
Well, thank you, Jared. The Delta IV Heavy, that's the one that lights itself on fire when it takes off.
Yeah, builds up a huge amount of hydrogen below it to start up the turbo pumps in its engine, and it ignites that hydrogen, and a big column of fire, almost 150 feet long, traverses up it. And that's why it's one of my favorite rockets. It lights itself in order to get going.
Yeah, it's an amazing vehicle, and didn't know that was going to be the last launch. I may have to, you'll have to remind me about these as I get busier and busier with things, but I might have to make a couple of trips up there. So thank you so much. Wonderful job without to launch this month. Now, I'm going to finish up our show tonight by talking about that amazing result from the Event Horizon Telescope, or EHT, which is actually a global network of radio telescopes. That's right. These telescopes are scattered across the whole globe, and they're used all at once to take images of, well, outer space. And what they did before was take an image of a black hole. As you can see here, go forward here at M87, it's a galaxy 55 million light years away, and they were able to peer down into the center of that, and they were imaged a black hole that weighs 6.2 billion suns, or solar masses, as we like to say. So if you compacted 6.2 billion of our suns into one little tiny space, that's what you get on the right-hand side. And they were able to image the glowing gas that's circulating around that black hole. Now, they do this by using a whole bunch of telescopes scattered across the globe, like I said. Now, notice these are more like radio dishes. This wavelength is about a little over 1 millimeter in size, so it's much longer than even infrared light, but it's not quite as long as true radio waves. Radio radiation can be meters long. So these ones, they're kind of in between. They're called submillimeter telescopes, although this is really in the millimeter range that they're being operated, and some are on top of Kit Peak, others are in Hawaii, some are in Spain, as you see there, so they're really scattered throughout the globe. And we can see here locations for many of them, and that South Pole telescope that Katie showed in that image is an important one because it can keep a continuous view of things as other ones rotate in and out of view. And it's actually important that they do that because that baseline, as we call it, the line between the two telescopes, changes as the Earth rotates. You can see the shape of that triangle is changing, and as new telescopes come online and are able to view things, you get different what we call baselines, and that's how we increase the resolution of these telescopes. If you just had 3 telescopes, you'd have really lousy resolution, but by having multiple ones that are rotating around and those baselines are changing, you can get very, very high resolution images out of this array of telescopes. Now, the new target, the one they announced, was in our own galaxy, about 26,000 light years away, and it's called Sagittarius A star. Very clever name. Astronomers always come up with things, but it is the massive black hole, about 4 million solar masses, so 4 million suns squeezed down together to make a black hole in the center of our galaxy. Andrea Ghez and Gensler won the Nobel Prize by watching stars orbit around it, around this spot that had nothing there. But now we have a picture of what's there in this millimeter wavelength. So let's take a look here. This is the view from here on Earth. That's our Milky Way. If you've ever been out camping or out in a dark sky, you can see the Milky Way band crossing it. And the center of the Milky Way is right there. Now let's zoom in. You can see the constellations that are around there, Scorpius, and the teapot of Sagittarius kind of points. The teapot, the nose of it, points down towards where our black hole is. And we're going to zoom into it here, getting closer and closer, passing some gas clouds as we zoom in further. And we'll continue to go in, and you can see those dark dust clouds that block light as well. And then finally, we end up there. Now, where's the black hole? I don't see a black hole, but there's lots and lots and lots of stars there. There it is. That's the location. When you use the Hubble Space Telescope, when you use other instruments, you can really zoom in and see it. In fact, here's an image of stars. Now, if we move in, here's a Hubble image using WIPIC 3, using the infrared part of the camera that can peer past some of that dust, but we still don't see the black hole there. You could use adaptive optics with Keck to be able to map the stars going around in the very, very center to get very high resolution images. But also, there's a lot of high energy gas clouds. It's a very turbulent area, so the light that's coming from the black hole is being moved around and wobbled. So that was one of the difficulties in getting this image. You have to stare through all this stuff. So here are the telescopes, or at least some of the ones that are looking at it. It's an artist's rendition of including a bunch of them here. And you can see our galaxy there, the bulge of it, and the black holes in there. So let's see what the image looked like. And there it is. It looks like a donut. It looks a lot like that M87 image. We were a little bit surprised it looked like this because in order to look like a donut here, it had to be pointed somewhat at us. We're not looking at edge on. We are looking at it kind of down the tube. The gas is going around in a circle. It can only be about 30 degrees off of being flat towards us in order to see it as a complete circle like this. And they're quite confident that this indeed is the right image. They did many different combinations. They did a lot of work to understand this, and this amazing image is there. Now, some folks will say, why is it so blurry? It looks blurry to me. This is just, a poor image. Can't they put some glasses on it like they did Hubble? Well, let's put it into context. We'll go here and we'll zoom in towards the galactic center. We'll put the moon in the way, though, just to be interesting. So it's not the size of the moon we're imaging. That's easy. It's not the size of craters on the moon. It's not the size of a small crater. It's not the size of boulders on the moon. Not the size of small rocks. Not the size of pebbles. It's the size of a donut. So yes, indeed, if you had a donut on the moon that gave off 1.3 millimeter length radiation, you would be able to see it with this telescope, with the resolution we have. So you might think that's blurry, but in reality, it's an amazing feat to be able to pick up something as small as a donut on the moon. It's really incredible they were able to do it. So I mentioned one of the problems with seeing this was the fact that there's gas and dust in the way, and hot gas is making the radiation change directions. The other problem is this is a small black hole. The material orbiting it only takes from minutes to hours to make a full circle around it. So as the gas gets close, it gets compressed, it heats up, it glows, but that glowing pattern was constantly changing. So the image that we see is actually more of an average. They had to average things together. They had to combine things over 5 days of observations in early April 2017 and work with it with supercomputers and really understand what happens to the light as it travels to us and also what was happening as it was orbiting the black hole. Now you can see that emission ring of the glowing material. The black hole's event horizon is smaller than that emission ring. It's actually about 2.5 times smaller. And that's the place that if you fell into, you wouldn't come out. And that makes sense why we're able to see that glow around it. Because, well, if it were inside of it, the light couldn't get out. So this material has not fallen in yet. Another thing they noticed was our black hole is being kind of what we call quiescent. It's not gobbling up a lot of that gas. It would be brighter if it were doing that. And it would also have a jet of material it was shooting out if it was eating material currently. So they put it on the equivalent of a human being on a diet of eating a grain of rice. And I forget whether it was a month or per year, but our black hole is barely eating any of the gas that's swirling around it. So a lot more could be learned from these images, and they're even going to be able to make some movies of this material moving around as they continue to study it. Now let's compare it to the M87 image. M87, like I said, is 55 million light years away. Sagittarius A star is only about 27,000 light years away. M87's black hole weighs 6.2 billion suns. The one in our galaxy is about 4 million suns. So when you do the math, ours in the sky is a little bigger on the sky than the M87 one. M87 would be a small donut. Ours would be a little bit of a bigger donut. And these images represent how big they are compared to each other. And the M87 one weighs about 1,600 times more than the one in Sagittarius A star, in our own galaxy. So it's a much bigger black hole. The material takes a much longer time to go around, which is why they could process that image first, and they managed to get that result out earlier than the Sagittarius A star. It was easier data to work with. So nonetheless, the Event Horizon Telescope comes through again, provides us with concrete proof and an image of our own black hole, whereas we knew it had to be there. There had to be something there the stars were orbiting. Well, now we know it really is a black hole, it really is glowing, and it matches a lot of the models. And indeed, meow, you're hearing my cat in the background. So I guess that means it's time for us to wrap up here and move on to our final slide, which is telling you all that Signs of Life, our brand new show in the Samuel Ocean Planetarium, is now playing. It's open to the public. So if you're in Southern California, you can show up. You can go to Griffith Observatory, get yourself a ticket, and see this spectacular new show. It's unlike anything I've seen in a planetarium dome before. The quality of the images and the animations is just, it's matched to our projectors. It's an 8K dome over your head. It's an amazing, amazing feat that's incredible. I recommend everybody that can go see it. And members of Griffith Observatory Foundation that supports us with this show and so much we do, you can skip the line. You can join today and you can skip the line. You get a lot of other benefits as well, but that's just one of them. So I highly recommend you take a look at that. So I'd like to thank, once again, our guest, Jim Gilletic, Deputy Project Manager of HST Hubble. Fantastic presentation tonight. Our audience loved it. They were raving about it in our YouTube chat. Patrick, I want to thank you, of course, for the Sky Report and all that you do to remind people of what to do and where to look in the sky. Jared, fantastic job with the Out to Launch this month. We really appreciate you stepping in for Chris. Katie, as always, thank you so much for all the production you do to make this show a success and to make this PowerPoint work. And then, of course, the work you do with the pretty pictures and the space weather. And then I do also want to thank all our tech staff that make it happen. Matthew, Brendan is up there as well. I'd like to thank our moderators, Haley, Alan, and also Daniel, moderating folks and making sure our chat stays polite and stays interested in the astronomy. But I just want to thank our whole Griffith Observatory team, Hannah and Bill, who do the introduction and the music. Again, fantastic job tonight. All of that is written just for our show. So I'm very lucky to to be part of this amazing team and have so many folks that work so hard to make this happen. So thank you, everybody. I very much appreciate it. And we're going to move on now and end the show. So good night, everybody. Well, one last thing. We won't see you live next month. We're going to take a month off in July. It's close to the 4th of July holiday. We all need a break. We will produce some things that we will load up that will be launched at showtime. Like Patrick will record a sky report that will include, maybe we'll do some space shorts and put some of those together for folks to see, but we won't have a full show. We won't be live, but we do recommend you subscribe, hit the notification button, and then when it does go live, you'll be told that you can come watch it on YouTube. And then we'll return to a live show in the beginning of August. So just so you know, that's going to be happening. You can catch us live on the summer solstice, however. We will have a live broadcast where we bring you local solar noon and also the sunset live. And if the sky is clear, we might even do some observing and try and show off some of what's up in the sky. So thank you, everybody, and have a wonderful month.
Thank you.